On the morning of October 3, 1942, a group of German engineers, staring through periscope slits at a machine that looked like nothing the world had ever seen. It was 14 meters tall, painted in a black and white checkerboard pattern so that its roll could be tracked by cameras. It weighed nearly 13 tons, most of which was alcohol and liquid oxygen. It stood on a simple steel launching table in a clearing surrounded by pine forest, wisps of vapor curling from its midsection where the cryogenic oxygen boiled against the autumn air. The men in the bunker had watched 2 previous attempts to launch this machine. Both had failed. The first in June had crashed after the engine cut out at less than a second of flight. The second in August had flown beautifully for 45 seconds before breaking apart at the speed of sound, pieces raining down into the sea. The head of the program, a 30-year-old aristocrat with a gift for engineering and an alarming willingness to work for anyone who would fund his obsession, had told his team that morning that this flight would determine whether the program survived or was cancelled. His name was Werner von Braun, and the machine on the pad was designated Aggregate 4. The world would come to know it as the V2. The countdown reached 0. Flame erupted from the base of the rocket, not the clean, bright flame of a welding torch, but a ragged, roaring column of fire that seemed almost to engulf the machine before it began to move. For an agonizing moment it sat there, balanced on its pillar of flame, rising so slowly that several observers later said they thought it was going to tip over. Then it cleared the launch table, then it cleared the trees. Then it was climbing, accelerating, punching through a thin layer of cloud, the roar of its engine rolling across the flat coastal landscape like sustained thunder. 1 minute into the flight, it reached the speed of sound. This time it did not break apart, it kept climbing. The engine burned for 68 seconds, pushing the rocket to a velocity of 1,341 meters per second, nearly 4 times the speed of sound, before cutting off. The V2 coasted upward on its momentum, arcing through the stratosphere to a peak altitude of 84.5 kilometers. It was the edge of space. When the tracking data confirmed what had happened, the room erupted. Walter Dornberger, the military officer overseeing the program, turned to his colleagues and said something that was both prophetic and, given the context of who was paying for this work, deeply unsettling. Today the spaceship was born. He was right, though not in the way he intended. The V2 was built to carry a 1-ton warhead, not astronauts. It was designed to terrorize cities, not to explore the cosmos. Within 2 years, more than 3,000 of them would rain down on London, Antwerp, and other targets, killing approximately 9,000 people, while more than 12,000 concentration camp prisoners would die manufacturing them in underground factories. The rocket that would open the door to space was born in one of the darkest chapters of human history, and its creator would spend the rest of his life trying to outrun that fact. But the V2 did not spring from nothing. The idea of using a directed stream of hot gas to propel an object, the fundamental principle behind every rocket ever built, is at least 8 centuries old and probably older. To understand how humanity got from the first crude fire arrows to the machine that stood on that Baltic launch pad, and from that machine to the reusable rockets landing on drone ships in the Atlantic Ocean today, you need to understand both the history and the physics, because they are inseparable. Every advance in rocketry was driven by a deeper understanding of the forces involved, and every failure, and there were spectacular failures, taught the engineers something about the unforgiving physics of turning chemical energy into motion. The story begins with black powder. Sometime in the 9th century, the exact date is lost, Chinese alchemists searching for an elixir of immortality stumbled upon a mixture that was the precise opposite of what they were looking for. They mixed saltpeter, potassium nitrate, with sulfur and charcoal, and the result was a substance that burned with violent self-sustaining fury. Unlike wood or oil, which need a constant supply of air to burn, this mixture carried its own oxidizer. The saltpeter provided the oxygen, the charcoal and sulfur provided the fuel. Once ignited, it would burn in a sealed container, in a cave, underwater, anywhere. It did not need the atmosphere. This single property, the ability to burn without external air, is what makes a rocket possible, and it is what separates a rocket from every other form of propulsion ever invented. The Chinese initially used black powder for fireworks and signals, but by the 13th century military applications had emerged. The first recorded use of rocket-propelled weapons dates to 1232, during the siege of Kaifeng, when the defending Song dynasty forces reportedly used arrows propelled by tubes of burning black powder against the invading Mongols. These were not sophisticated devices. They were bamboo tubes packed with powder, attached to sticks for stability, and they were wildly inaccurate, but they flew. They covered distances that no arrow launched by a bow could match. And the noise and fire they produced had a psychological effect on enemy troops that was, by some accounts, as devastating as their physical impact. The principle at work in these crude weapons is the same principle that launches a Falcon 9 rocket from Cape Canaveral today, Newton's third law of motion, which states that for every action there is an equal and opposite reaction. When the burning powder inside the tube produces hot gas, that gas expands in all directions, pressing equally against the walls of the tube, but the tube has a hole at one end, the nozzle, though the Chinese would not have used that word, and at that end the gas escapes. On the opposite end the wall is solid and the pressure pushes against it with no counterbalancing force on the other side. The net effect is a force that pushes the tube in the direction opposite to the escaping gas. The gas goes backward, the rocket goes forward. No air is needed, no ground is needed, no medium of any kind is needed for the rocket to push against. It pushes against its own exhaust. This is a subtle and easily misunderstood point. Many people, even today, believe that a rocket works by pushing its exhaust against the air behind it, the way a jet boat pushes water backward to move forward. This is wrong. A rocket works by expelling mass. If you are standing on a frozen pond wearing ice skates and you throw a bowling ball as hard as you can, you will slide backward. The ball goes one way, you go the other. You're not pushing against the air, you're not pushing against the ice, you're pushing against the ball, and the ball is pushing back against you. A rocket does the same thing, but instead of a bowling ball, it throws trillions of gas molecules per second, each one individually tiny but collectively enormous in their effect. This is also why an ordinary car engine, an internal combustion engine, the kind that powers your vehicle, cannot work in space. Not because there is no oxygen in space, though there is not. A car engine could in principle be supplied with its own oxygen just as a rocket carries its own. The reason a car engine is useless in space is that a car engine produces rotational motion, a spinning crankshaft, not thrust. It is designed to turn wheels which push against the ground. In space, there is no ground, there are no wheels, there is nothing to push against except what you brought with you. A rocket engine converts chemical energy directly into a directed stream of high-velocity gas, and the reaction force of that gas is thrust. It is the only form of propulsion that works in a vacuum. The Chinese fire arrows spread along the Silk Road, reaching the Arab world and then Europe by the late 13th century. For several centuries, rockets remained a curiosity, used occasionally in warfare, more often in celebrations and never with any particular reliability or range. The problem was control. A tube of burning powder on a stick does not fly straight. It wobbles, it veers, it corkscrews. The stick provides some stabilization, the way feathers stabilize an arrow, but the effect is crude and unpredictable. Serious military planners preferred cannons, which were far more accurate and could deliver heavier payloads. Rockets were unreliable, temperamental, and generally regarded as more of a hazard to their operators than to the enemy. This began to change in the late 18th century, when the armies of the Kingdom of Mysore in southern India used iron-cased rockets against the British East India Company with considerable effectiveness. The Mysorean rockets were a significant advance over earlier designs. The iron casing allowed higher internal pressures which produced more thrust and longer range. Some could travel up to 2 kilometers. The rockets were deployed in large salvos, compensating for their individual inaccuracy with sheer volume of fire. At the Battle of Seringapatam in 1799, British troops were badly shaken by the Mysorean rocket barrage, and a British officer named William Congreve took several captured specimens back to England for study. Congreve was fascinated. Over the next decade, he developed an improved design, larger, more powerful, with better stabilization and a range of several kilometers. The Congreve rocket was deployed by the British military throughout the Napoleonic Wars and beyond. It was a Congreve rocket barrage that inspired the line about the rocket's red glare in what would become the American national anthem, describing the British bombardment of Fort McHenry in Baltimore during the War of 1812. Congreve rockets were used in the Napoleonic Wars, in colonial campaigns across Asia and Africa, and in the Crimean War. They were spectacular but still wildly inaccurate, and by the mid-19th century, improvements in artillery, rifled barrels, explosive shells, better metallurgy had made the cannons so effective that rockets fell out of military favor almost entirely. For the rest of the 19th century and into the early 20th, rockets were relegated to the margins of technology, used for maritime rescue, for carrying lines to ships in distress, for launching signal flares, and for entertainment. Nobody serious thought of them as a means of transportation, let alone a means of reaching space. Nobody except 3 men working independently in 3 different countries, who between them would invent the theoretical and practical foundations of modern rocketry. Their names were Konstantin Tsiolkovsky, Robert Goddard, and Hermann Oberth. None of them was wealthy, none of them had powerful institutional backing. All 3 were, to varying degrees, regarded as eccentrics or cranks by their contemporaries. And all 3 understood something that almost no one else did, that a rocket, if properly designed, could reach space. Not in theory, not in fantasy. In engineering reality, Tsiolkovsky was a Russian schoolteacher, nearly deaf from a childhood illness, who worked in isolation in the provincial town of Kaluga, south of Moscow. In 1903, the same year, the Wright brothers flew at Kitty Hawk. He published a paper titled The Exploration of Cosmic Space by Means of Reaction Devices, in which he derived the fundamental equation of rocketry. The Tsiolkovsky rocket equation, as it is now known, relates the change in velocity of a rocket to the exhaust velocity of its propellant, and the ratio of the rocket's initial mass to its final mass after the propellant has been consumed. It is one of the most important equations in all of engineering, and it is brutally unforgiving. The equation says this: the change in velocity you can achieve, the delta V in the jargon of rocket science, is equal to the exhaust velocity multiplied by the natural logarithm of the mass ratio. The mass ratio is the fully fueled mass divided by the empty mass. The natural logarithm is a function that grows very slowly. To double your delta V, you do not need to double your mass ratio. You need to square it. To triple your delta V, you need to cube it. This means that achieving high velocities requires either very high exhaust velocities or very large mass ratios, or both. And here's the cruelty. The structural mass of the rocket, the tanks, the engines, the plumbing, the payload, is dead weight that contributes nothing to thrust but must be accelerated along with the propellant. The heavier the structure, the worse the mass ratio and the less velocity you can achieve. For a chemical rocket, burning the most energetic propellants available, liquid hydrogen and liquid oxygen, the exhaust velocity is about 4,400 meters per second. To reach low Earth orbit, you need a delta V of about 9,400 meters per second. Plug these numbers into the Tsiolkovsky equation and you find that the mass ratio required is about 8.5, meaning that for every kilogram of payload and structure you want to put in orbit, you need about 7.5 kilograms of propellant. For a rocket the size of the Saturn V, which put astronauts on the moon, this means that at liftoff, more than 85% of the vehicle's mass is propellant. The rocket is essentially a flying fuel tank with a small payload perched on top. Tsiolkovsky understood this. He also understood the solution, staging. Instead of building one enormous rocket, you build several smaller rockets stacked on top of each other. The bottom stage fires first, accelerating the entire stack. When its propellant is exhausted, it is jettisoned, dropped away, taking its empty tanks and engines with it, removing their dead weight from the equation. The second stage then fires, accelerating a much lighter vehicle. The process can be repeated as many times as needed, with each stage discarding its dead weight and the remaining stages achieving progressively higher velocities. Staging is what makes orbital spaceflight possible with chemical propellants. Without it, the mass ratios required would be so enormous that no practical rocket could be built. Tsiolkovsky also proposed the use of liquid propellants, specifically liquid hydrogen and liquid oxygen, instead of solid black powder. His reasoning was sound. Liquid propellants can be mixed and burned in a controlled manner, allowing the engine to be throttled, shut down, and restarted. Solid propellants, once ignited, burn until they are exhausted. You cannot stop them. You cannot control the rate of burn with any precision, and their exhaust velocities are lower than what can be achieved with the best liquid propellants. Liquid rockets are more complex, more difficult to build, and more prone to failure, but they are far more capable. Tsiolkovsky published his ideas over several decades, but he never built a rocket. He was a theorist, not an experimentalist, and he lacked the resources and institutional support to translate his equations into hardware. That task fell to Robert Goddard. Goddard was an American physicist, a professor at Clark University in Worcester, Massachusetts, and he was as secretive and suspicious as Tsiolkovsky was dreamy and philosophical. Goddard understood that the scientific establishment would ridicule his work, which it did, and he protected his ideas with a ferocity that bordered on paranoia. He filed patents obsessively, published reluctantly, and shared his data with almost no one, but he built rockets. Real rockets. Working hardware that flew. On March 16, 1926, on a snow-covered farm in Auburn, Massachusetts, Goddard launched the first liquid-fueled rocket in history. It was a spindly, ungainly contraption, a framework of metal tubes supporting a combustion chamber and nozzle at the top, with the fuel and oxidizer tanks below. It burned gasoline and liquid oxygen. It flew for 2.5 seconds. It reached an altitude of 12.5 meters. It traveled a horizontal distance of 56 meters. It landed in a cabbage patch. It was the most important flight since Kitty Hawk. Over the next 15 years, working largely alone or with a small team in the New Mexico desert, Goddard developed progressively more sophisticated rockets. He invented the gyroscopic guidance system. He developed the vane system for steering, small metal vanes placed in the rocket exhaust, which could deflect the flow and change the rocket's direction. He experimented with turbopumps to force propellant into the combustion chamber at high pressure. He developed regenerative cooling, a technique in which the fuel is circulated through channels in the combustion chamber and nozzle walls before being injected and burned, absorbing heat from the walls and preventing them from melting. Every one of these innovations would prove essential to the development of large-scale rocketry. Every one of them was independently reinvented by the German team that built the V2, because Goddard refused to share his work. The third member of the founding trinity was Hermann Oberth, a Romanian-born physicist of German descent who published a landmark treatise in 1923 called Die Rakete zu den Planetenräumen, The Rocket into Planetary Space. Oberth's work was more rigorous and detailed than Tsiolkovsky's, and it reached a wider audience. Among those it influenced was a young German engineering student named Wernher von Braun, who joined a rocket society in Berlin and eventually attracted the attention of the German military. The German army was interested in rockets for a specific and cynical reason. The Treaty of Versailles, which ended World War I, prohibited Germany from developing long-range artillery. It said nothing about rockets. The military saw rocketry as a loophole, a way to develop long-range weapons that did not technically violate the treaty. Funding was provided. A development center was established at Peenemünde on the Baltic coast, and von Braun, still in his 20s, was put in charge. What von Braun and his team built at Peenemünde was, in engineering terms, a quantum leap beyond anything that had come before. The V2 was not a scaled-up firework. It was a precision machine, the first large-scale liquid-fueled rocket, the first ballistic missile, and the first human-made object to reach the edge of space. Its engine, designated the A4, burned a mixture of 75% ethanol and 25% water with liquid oxygen, producing a thrust of about 270 kilonewtons for approximately 65 seconds. The combustion chamber operated at a pressure of about 15 atmospheres and a temperature of roughly 2,700 degrees Celsius, hot enough to melt steel, hot enough to destroy any material known at the time. How do you prevent a combustion chamber from melting when the gases inside it are thousands of degrees hotter than the melting point of the chamber walls? This is one of the central engineering challenges of rocketry, and the V2 engineers solved it using a combination of techniques that remain fundamental to rocket engine design today. The first technique is film cooling. A thin layer of propellant, in the V2's case the ethanol-water mixture, is injected along the inner wall of the combustion chamber through a ring of small holes. This liquid film evaporates as it absorbs heat from the wall, creating a cooler boundary layer of gas between the wall and the main combustion zone. The film does not prevent heat transfer entirely, but it reduces it enough to keep the wall temperature below the melting point of the metal. The second technique, which Goddard had pioneered and the V2 engineers adopted, is regenerative cooling. The fuel is circulated through a jacket of narrow channels surrounding the combustion chamber and nozzle before being injected into the chamber for combustion. As the fuel flows through these channels, it absorbs heat from the walls, cooling them. The fuel itself is preheated in the process, which actually improves combustion efficiency, since warmer fuel vaporizes more readily and burns more completely. It is an elegant solution. The thing that would destroy the engine is used to cool it, and in the process it becomes better fuel. The combustion chamber is where the magic happens, but it is not where the complexity lies. The most complex component of a liquid-fueled rocket engine, the component that has caused more failures, more redesigns, more sleepless nights for more engineers than any other, is the turbopump. A liquid rocket engine needs to get its propellant, fuel and oxidizer from the tanks into the combustion chamber. This sounds simple. It is not. The combustion chamber operates at high pressure. In modern engines, pressures of 100 to 300 atmospheres are common. The propellant in the tanks is at much lower pressure. Something has to force the propellant from the low-pressure tanks into the high-pressure chamber against the pressure gradient at flow rates measured in hundreds of kilograms per second. That something is the turbopump. A turbopump is, in essence, a pump driven by a turbine. The turbine is spun by hot gas, usually generated by burning a small amount of the same propellants that the engine uses in a device called a gas generator or a preburner. The turbine drives the pump, which forces the propellant into the combustion chamber. The concept is straightforward. The engineering is diabolical. Consider the numbers. The turbopump for the Space Shuttle main engine, the RS-25, one of the most sophisticated rocket engines ever built, spins at approximately 37,000 revolutions per minute. Its liquid hydrogen pump delivers fuel at a rate of about 70 kilograms per second, at a discharge pressure of about 450 atmospheres. The power output of the turbopump assembly is roughly 55,000 kilowatts, about 74,000 horsepower, from a device that you could fit on a large dining table. Per unit of size and weight, it is the most powerful mechanical device ever constructed by human beings. The stresses inside a turbopump are almost beyond comprehension. The turbine blades spinning at tens of thousands of RPM in a stream of hot gas at temperatures approaching 900 degrees Celsius experience centrifugal forces that would tear apart any conventional material. They are made of single crystal nickel superalloys, metals grown as a single unbroken crystal, with no grain boundaries where cracks could initiate. The bearings must support enormous loads while spinning at speeds that generate enough friction to melt them in seconds without adequate lubrication. In many cryogenic turbopumps, the propellant itself, liquid hydrogen at minus 253 degrees Celsius, or liquid oxygen at minus 183 degrees Celsius, serves as the lubricant and coolant for the bearings. The engineering tolerances are measured in micrometers. A particle of dust in the wrong place can cause a catastrophic failure. The history of rocketry is, in large part, a history of turbopump failures. Turbopumps have exploded, seized, cavitated, overheated and shattered. The F-1 engine that powered the first stage of the Saturn V rocket, the largest and most powerful rocket engine ever flown, went through years of development during which combustion instability in the main chamber caused repeated violent failures. The problem was not the turbopump itself, but the injector, the component that sprays fuel and oxidizer into the combustion chamber in a pattern that promotes rapid, uniform mixing and burning. If the mixing is uneven, pockets of fuel-rich or oxidizer-rich gas can form, and these pockets can oscillate at acoustic frequencies, setting up standing waves in the chamber that amplify themselves in a vicious feedback loop. The pressure oscillations can reach thousands of atmospheres, tearing the engine apart in milliseconds. The F-1 injector problem was eventually solved by a combination of empirical testing and inspired guesswork. Engineers would deliberately trigger instabilities by detonating small bombs inside the combustion chamber during test firings, then study high-speed films and pressure data to understand how the instability developed and how to suppress it. They tried different injector patterns, different baffle configurations, different chamber geometries. It took years. When they were done, the F-1 was the most reliable large rocket engine in the world, and the Saturn V compiled a perfect flight record, 13 launches, 0 failures. The V2's turbopump was primitive by comparison, a single shaft unit driven by hydrogen peroxide decomposition, producing a modest power output at modest pressures. But it worked, and it established the basic architecture that every large liquid rocket engine would follow: tanks, turbopumps, injectors, combustion chamber, nozzle. The nozzle deserves special attention because it is where the thermal energy of the combustion gases is converted into the kinetic energy of directed motion, where heat becomes speed. And the design of the nozzle is governed by one of the most beautiful and counterintuitive results in fluid dynamics. In the mid-19th century, a Swedish engineer named Gustav de Laval was working on a prosaic problem: how to design a more efficient steam turbine for the cream separator industry. He discovered that if a converging duct, a funnel shape, was followed by a diverging duct, a bell shape, the steam flowing through the device would accelerate to supersonic speeds in the diverging section far faster than was possible with a simple converging nozzle alone. This result seems paradoxical. In everyday experience, fluids speed up when they flow through a constriction. Think of a garden hose with your thumb over the end. How can a fluid accelerate in a section where the duct is getting wider? The answer lies in the difference between subsonic and supersonic flow. At subsonic speeds, a gas behaves more or less like a liquid. It is nearly incompressible, and it speeds up when the duct narrows. But at supersonic speeds, the gas is highly compressible. Its density changes dramatically with pressure, and the relationship between duct area and flow velocity reverses. In the diverging section of a de Laval nozzle, the gas expands, its pressure drops, and it accelerates. The narrowest point of the nozzle, the throat, is where the gas transitions from subsonic to supersonic. At the throat, the gas velocity is exactly equal to the local speed of sound. This is called the choked condition, and it is a fundamental feature of all rocket nozzles. The shape of the diverging section determines the exit velocity of the gas, which in turn determines the thrust and efficiency of the engine. A longer, more gradually diverging nozzle produces a higher exit velocity, but it also makes the nozzle larger and heavier. The optimal shape is a trade-off between performance and weight, and it depends on the altitude at which the engine operates. At sea level, atmospheric pressure pushes back against the exhaust, and a shorter nozzle is optimal. In the vacuum of space where there's no atmospheric back pressure, a much longer, more fully expanded nozzle gives the best performance. This is why the engines on the upper stages of rockets, the stages that fire in the vacuum of space, have enormous bell-shaped nozzles, while the engines on the first stage, which must operate at sea level, have smaller ones. Every rocket nozzle you have ever seen, the great flaring bells of the Saturn V's first stage F1 engines, the compact nozzle clusters of the Falcon 9's Merlin engines, the single enormous vacuum-optimized nozzle of the Raptor vacuum on Starship's upper stage is a de Laval nozzle. The principle is the same. The Swedish cream separator engineer's discovery, made in the service of the dairy industry, became the throat through which the space age was born. After the war ended in 1945, the V2 and its creators became the most sought-after prizes of the victorious powers. The United States captured von Braun and most of his senior engineers, along with enough V2 components to assemble roughly 70 complete rockets. The Soviet Union captured the production facilities, many of the technicians, and enough documentation to reverse engineer the design. Both countries immediately began launching captured V2s and developing their own improved versions. The early post-war years were a period of rapid experimentation. In the United States, V2s were launched from White Sands, New Mexico, carrying scientific instruments into the upper atmosphere for the first time. In the Soviet Union, captured German engineers worked alongside Soviet teams to build the R1, a direct copy of the V2, and then the R2, which doubled its range. By the early 1950s, both countries had moved beyond the V2 design entirely, and the race to build intercontinental ballistic missiles, rockets powerful enough to deliver nuclear warheads across oceans, had begun in earnest. The propellants used in these early missiles varied widely, and the choice of propellant reveals much about the engineering philosophy and practical constraints of the time. The V2 used ethanol and liquid oxygen. Ethanol was chosen partly because it was readily available in wartime Germany. It could be distilled from potatoes, and partly because its relatively low combustion temperature simplified the engineering of the combustion chamber and nozzle. The mixture was diluted with 25% water, specifically to reduce the flame temperature further and ease the cooling problem. The performance penalty was accepted because the engineers did not have materials or cooling techniques adequate to handle a hotter burning propellant. Kerosene, a refined petroleum product, essentially a purified form of jet fuel, became the propellant of choice for many post-war rockets. It is denser than ethanol, which means smaller, lighter tanks for the same mass of propellant. It has a higher energy content per kilogram. It is stable, easy to handle, and available in enormous quantities. It does not need to be stored at cryogenic temperatures. Its main disadvantage is that it produces soot, carbon particles which can accumulate in the engine and degrade performance over time. For single-use engines, this is not a concern. For reusable engines, it becomes a significant maintenance issue. Liquid hydrogen is the highest performance chemical fuel available. When burned with liquid oxygen, it produces an exhaust velocity of about 4,400 meters per second, roughly 30% higher than kerosene oxygen. This translates directly into more delta V per kilogram of propellant, which means either more payload to orbit or a smaller, lighter rocket for the same payload. The upper stages of the Saturn V used liquid hydrogen, and it was the propellant that made the moon missions possible, but liquid hydrogen is a nightmare to work with. It must be stored at minus 253 degrees Celsius, just 20 degrees above absolute zero. At these temperatures, it is so cold that it can freeze the oxygen in the adjacent oxidizer tank. If the insulation is inadequate, it is the lightest element with a density of only 71 kilograms per cubic meter, which means that hydrogen tanks must be enormous to hold a useful mass of fuel. It leaks through seals and joints with infuriating ease because the hydrogen molecule is so small that it can diffuse through solid metal. And it is spectacularly flammable. Its flammability range in air extends from 4% to 75% concentration, and its ignition energy is about 1/10 that of gasoline. A static spark too small to feel can ignite a hydrogen-air mixture. Methane, the main component of natural gas, has recently emerged as a compromise between kerosene and hydrogen. Its exhaust velocity when burned with liquid oxygen is intermediate, about 3,600 meters per second, higher than kerosene but lower than hydrogen. It is denser than hydrogen, requiring smaller tanks, though not as dense as kerosene. It stores at a more manageable cryogenic temperature of minus 162 degrees Celsius. It burns cleanly, producing almost no soot, which is a major advantage for reusable engines. And it can potentially be manufactured on Mars from the carbon dioxide atmosphere and subsurface water ice using a process called the Sabatier reaction, a fact that has not escaped the attention of SpaceX, whose Raptor engines burn methane and whose long-term goal is the colonization of Mars. The chemistry of rocket combustion is, at its core, an oxidation reaction. The fuel combines with oxygen, releasing energy in the form of heat. The amount of energy released depends on the specific combination of fuel and oxidizer, and it can be calculated precisely from the thermochemistry of the reaction. For kerosene oxygen, the energy release is about 10.3 megajoules per kilogram of propellant mixture. For hydrogen oxygen, it is about 13.4 megajoules per kilogram. For methane oxygen, it is about 11.1 megajoules per kilogram. But the energy content of the propellant is not the whole story. What matters for rocket performance is not how much energy is released, but how effectively that energy is converted into exhaust velocity. The exhaust velocity depends on the temperature and the molecular weight of the combustion products. Higher temperature means faster moving molecules. Lower molecular weight also means faster moving molecules because lighter molecules move faster at any given temperature. Hydrogen oxygen produces the highest exhaust velocity, not because it releases the most energy per kilogram. It does, but only slightly more than methane, but because its combustion products are primarily water vapor, with a molecular weight of 18. Kerosene oxygen produces a mixture of water vapor and carbon dioxide, with an average molecular weight around 24. The lighter exhaust of hydrogen oxygen moves faster, and faster exhaust means more thrust per kilogram of propellant consumed. This is why rocket scientists obsess over a quantity called specific impulse, usually abbreviated ISPE and measured in seconds. Specific impulse is essentially the exhaust velocity divided by the acceleration of gravity at Earth's surface. It tells you how many seconds 1 kilogram of propellant can produce 1 kilogram of thrust. A higher specific impulse means a more efficient engine. Kerosene oxygen engines typically achieve a specific impulse of about 310 to 340 seconds at sea level. Hydrogen oxygen engines achieve about 420 to 450 seconds. The theoretical maximum for any chemical propellant combination is around 500 seconds, which is achieved by some exotic combinations, beryllium and oxygen, for instance, that are too toxic or too impractical for use in real rockets. These numbers specific impulse, exhaust velocity, mass ratio are the cruel arithmetic of spaceflight. They define the boundaries within which every rocket engineer must work, and they explain why getting to orbit is so difficult and so expensive. The energy required to accelerate a kilogram to orbital velocity, roughly 32 megajoules, is about the same as the energy content of a kilogram of gasoline. In principle, it should be cheap and easy to reach space. In practice, the tyranny of the rocket equation means that you must carry your propellant with you, and the propellant needed to accelerate the payload creates an exponential relationship between payload mass and total vehicle mass that makes spaceflight inherently, fundamentally, punishingly expensive. By the late 1950s, the ballistic missile programs of the United States and the Soviet Union had produced rockets powerful enough to reach orbit. The question was no longer whether it was possible, but who would do it first. The Soviet Union won. On October 4, 1957, a modified R-7 intercontinental ballistic missile, the world's first ICBM, designed by the legendary engineer Sergei Korolev, launched Sputnik 1 into orbit. It was a polished aluminum sphere 58 centimeters in diameter, equipped with two radio transmitters that broadcast a continuous series of beeps at frequencies receivable by any amateur radio operator. The beeping continued for 21 days until the batteries died. The satellite itself remained in orbit for 3 months before re-entering the atmosphere and burning up. The R-7 that launched Sputnik was a remarkable machine. It used kerosene and liquid oxygen, burning in 4 strap-on boosters surrounding a central core, a configuration that would become the basis for the Soyuz rocket family, which remains in service more than 6 decades later with more than 1,900 launches to its credit. It is the most launched rocket in history, and its basic design has changed remarkably little since the 1960s. The engines have been improved, the guidance systems modernized, the manufacturing processes refined, but the fundamental architecture, 4 strap-on boosters, central core, upper stages, is recognizably descended from Korolev's original R-7. The United States, stung by the shock of Sputnik, accelerated its own space program. Wernher von Braun, now working for the US, Army had been developing the Jupiter C rocket, which was capable of reaching orbit, but had been held back by political rivalries between the Army, Navy, and Air Force. After the Navy's Vanguard rocket, America's official satellite launcher, exploded on the launch pad in a humiliating televised failure in December 1957. Von Braun was given the go-ahead on January 31, 1958. His team launched Explorer 1, America's first satellite, on a Jupiter C rocket. Explorer 1 carried a cosmic ray detector designed by James Van Allen, and its data revealed the existence of the radiation belts that bear Van Allen's name, belts of energetic charged particles trapped by the Earth's magnetic field, a discovery with profound implications for future human spaceflight. The space race that followed was, at its core, a contest between two nations' engineering capabilities, played out in the most unforgiving environment imaginable. Each success built confidence and capability. Each failure, and there were many, taught painful lessons about the physics and engineering of space travel. The Soviet Union maintained its lead through the early 1960s. Yuri Gagarin became the first human in space on April 12, 1961, orbiting the Earth once in a Vostok capsule launched by a modified R-7. The flight lasted 108 minutes. Gagarin ejected from the capsule during re-entry and parachuted to the ground separately, a detail that the Soviet authorities initially concealed because the rules of the Fédération Aéronautique Internationale required the pilot to land with the spacecraft for the flight to be recognized as an official record. 3 weeks later, on May 5, 1961, Alan Shepard became the first American in space, launched on a Redstone rocket, essentially a scaled-up V-2 for a 15-minute suborbital flight that reached an altitude of 187 kilometers. It was an impressive achievement, but a modest one compared to Gagarin's orbital flight, and it underscored America's position as the runner-up in the space race. 20 days after Shepard's flight, President John F. Kennedy stood before a joint session of Congress and made one of the most consequential speeches of the 20th century. "I believe that this nation should commit itself to achieving the goal before this decade is out, of landing a man on the moon and returning him safely to the Earth." The speech was audacious at the time Kennedy delivered it. The total American experience with human spaceflight consisted of 15 minutes and 28 seconds. The technology needed to reach the moon did not exist. The rocket that would carry astronauts there had not been designed. The total cost of the program, ultimately about $25.4 billion in 1973 dollars, or roughly $200 billion in today's money, had not been estimated, let alone appropriated. Kennedy was committing the nation to a goal that most engineers privately regarded as nearly impossible within the specified time frame. They did it anyway. The rocket that made it possible was the Saturn V, designed by von Braun's team at the Marshall Space Flight Center in Huntsville, Alabama. It remains the most powerful rocket ever successfully flown. Fully fueled, it stood 110 meters tall, taller than the Statue of Liberty, and weighed approximately 2,950 metric tons. More than 85% of that weight was propellant. The first stage, the SIC, was powered by 5 F1 engines, each producing about 6.7 meganewtons of thrust, for a combined total of more than 33 meganewtons. Each F1 burned kerosene and liquid oxygen at a rate of approximately 2,600 kilograms per second. The 5 engines together consumed roughly 13 metric tons of propellant per second. The first stage burned for about 150 seconds, during which time it consumed approximately 2,100 metric tons of propellant and accelerated the vehicle to about 2,700 meters per second, roughly Mach 8, at an altitude of about 67 kilometers. The second stage, the S2, was powered by 5 J2 engines burning liquid hydrogen and liquid oxygen. The J2 was a marvel of engineering, the first large production rocket engine to use hydrogen fuel with a specific impulse of 421 seconds in vacuum. The second stage burned for about 6 minutes, boosting the vehicle to near orbital velocity at an altitude of about 185 kilometers. The third stage, the SIVB, used a single J2 engine. It burned twice, once to achieve orbital velocity and insert the spacecraft into a parking orbit around the Earth, and a second time the translunar injection burn to accelerate the spacecraft to the 10,800 meters per second needed to escape Earth's gravity and coast to the moon. The Saturn V flew 13 times between 1967 and 1973. Every flight was successful. 6 of them carried astronauts to the lunar surface. It was, and remains, the high water mark of chemical rocketry, the most powerful expression of the physics that Tsiolkovsky had outlined in his provincial study more than 60 years earlier. After Apollo, the focus of American human spaceflight shifted to the Space Shuttle, a partially reusable system that was supposed to make space access routine and affordable. It did neither. The shuttle was a remarkable engineering achievement in many ways. Its main engines, the RS-25, also known as the Space Shuttle Main Engine, or SSME, were the most advanced liquid rocket engines ever built. They operated at a chamber pressure of about 206 atmospheres, higher than any previous production engine, and achieved a specific impulse of 453 seconds in vacuum, the highest ever achieved by a hydrogen-oxygen engine in operational service. They were designed to be reused up to 55 times, and some individual engines flew more than 20 missions. The RS-25 used a propulsion cycle called staged combustion. which is significantly more efficient than the gas generator cycle used in the F-1 and most other engines of the Apollo era. In a gas generator cycle, a small fraction of the propellants is burned in a separate gas generator to drive the turbopump, and the turbine exhaust, hot but still combustible, is dumped overboard, wasting potential thrust. In a staged combustion cycle, the turbine exhaust is routed back into the main combustion chamber and burned again, extracting virtually all of the chemical energy from the propellants. This produces a higher chamber pressure and a higher exhaust velocity, but it also makes the engine far more complex and far more difficult to develop. The Soviet Union independently developed staged combustion engines, notably the RD-170 and its derivatives, which are among the highest performing engines ever built. The shuttle's main engines burn liquid hydrogen and liquid oxygen stored in a huge external tank, the large orange structure in launch images, which was the only major component of the shuttle system that was not reused. Flanking the external tank were two solid rocket boosters, each producing about 14 meganewtons of thrust, more than twice the thrust of a single F-1 engine. The solid boosters provided about 80% of the shuttle's thrust during the first 2 minutes of flight. Solid rocket boosters are in principle much simpler than liquid engines. There are no turbopumps, no injectors, no complex plumbing. The propellant, a mixture of ammonium perchlorate, the oxidizer, aluminum powder, the fuel, and a polymer binder that holds it together, is cast directly into the booster casing as a single enormous grain. When ignited, it burns from the inside out, producing a sustained blast of hot gas that exits through a nozzle at the base. The thrust profile is determined by the shape of the internal bore, the hollow channel through the center of the grain. A star-shaped bore produces high initial thrust that tapers off. A cylindrical bore produces constant thrust. The design is chosen to match the vehicle's needs. The simplicity of solid motors comes at a cost. Once ignited, they cannot be shut down. They cannot be throttled. If something goes wrong, there is no option to cut the engine and abort. The propellant grain must be manufactured with extreme care, because any cracks, voids, or imperfections can cause uneven burning pressure spikes and catastrophic failure. The joints between the booster segments, large solid rockets, are typically assembled from multiple cylindrical segments, must be sealed perfectly, because any leakage of hot gas can burn through the casing in seconds. On January 28, 1986, the Space Shuttle Challenger was destroyed 73 seconds after launch, killing all 7 crew members. The cause was a failure of a rubber O-ring seal in the joint between 2 segments of the right solid rocket booster. The overnight temperature at the launch pad had dropped to -8 degrees Celsius, far below the operating range for which the O-rings had been designed. The cold had stiffened the rubber, preventing it from sealing the joint properly. Hot combustion gases at approximately 3,300 degrees Celsius burned through the failed seal, impinging on the external tank. The tank ruptured, its propellants mixed, and the vehicle was destroyed by aerodynamic forces as it tumbled through the air at twice the speed of sound. The Challenger disaster was a failure not of physics but of decision-making. Engineers at Morton Thiokol, the company that manufactured the boosters, had warned NASA the night before the launch that the cold temperatures could compromise the O-ring seals. Their warnings were overruled by managers who were under pressure to maintain the shuttle's launch schedule. The lesson that the laws of physics do not bend to institutional pressure, that the universe does not care about your schedule, was paid for with 7 lives. 17 years later, on February 1st, 2003, the Space Shuttle Columbia broke apart during re-entry, killing all 7 crew members during launch. A piece of insulating foam had broken free from the external tank and struck the leading edge of the orbiter's left wing, damaging the thermal protection tiles. During re-entry, superheated atmospheric gases entered through the damaged area and destroyed the wing's internal structure. The orbiter lost control and disintegrated at an altitude of about 60 kilometers, traveling at approximately 19,000 kilometers per hour. The Columbia disaster ended any remaining illusions about the shuttle as a routine transportation system. The program continued for another 8 years, completing assembly of the International Space Station, but the decision to retire the shuttle was effectively made in the aftermath of the Columbia investigation. The final shuttle mission flew on July 8, 2011. The Space Shuttle was supposed to reduce the cost of spaceflight. It did not. Over its 30-year operational life, the program flew 135 missions at an average cost of approximately $1.5 billion per launch, roughly $54,000 per kilogram of payload, to low Earth orbit. This was more expensive, not less than the expendable rockets it was designed to replace. The partial reusability of the shuttle, the orbiter and solid rocket boosters were recovered and refurbished, while the external tank was discarded, saved less money than the refurbishment process cost. The dream of cheap, airline-like access to space remained unfulfilled. The dream did not die. It moved to Hawthorne, California, where a South African-born entrepreneur named Elon Musk had founded a company called Space Exploration Technologies Corporation, SpaceX, in 2002, with the stated goal of reducing the cost of spaceflight by a factor of 10 and eventually enabling the colonization of Mars. Musk's approach was radical in its simplicity: build everything in-house, iterate rapidly, accept failure as a learning tool, and make the rocket reusable. Not partially reusable like the shuttle, where recovery and refurbishment costs ate up the savings. Fully reusable, where the rocket lands itself, is inspected, refueled, and flies again like an airplane. The first 3 flights of SpaceX's Falcon 1 rocket failed. The company was nearly bankrupt. The 4th flight on September 28, 2008, succeeded, placing a dummy payload in orbit and making the Falcon 1 the first privately developed liquid-fueled rocket to reach orbit. Musk later said that the company had enough money for exactly one more attempt. If the 4th flight had failed, SpaceX would have ceased to exist. The Falcon 9, SpaceX's workhorse rocket, first flew in 2010. Its 9 Merlin engines, burning kerosene and liquid oxygen in a gas generator cycle, produce a combined sea-level thrust of about 7.6 meganewtons. The engine is not the most advanced or highest-performing rocket engine ever built. Its specific impulse of 282 seconds at sea level is adequate but unremarkable. What makes it extraordinary is its reliability, its manufacturability, and the fact that it can land itself. The first successful landing of a Falcon 9 first stage occurred on December 21, 2015 at Cape Canaveral. After boosting its upper stage and payload toward orbit, the first stage, a 41-meter-tall, 25-metric-ton aluminum cylinder, reignited its engines, performed a series of boost-back, entry and landing burns, deployed 4 titanium grid fins for aerodynamic control, extended 4 landing legs, and touched down vertically on a concrete pad, balanced on a single-center engine, with a velocity at touchdown of less than 2 meters per second. The entire landing sequence from upper stage separation to touchdown took about 8 minutes. It was a moment that changed the economics of spaceflight. A Falcon 9 first stage costs approximately $30 million to manufacture. Before reusability, that $30 million was thrown away after every flight. A 15-story machine used once deliberately crashed into the ocean. With reusability, the same stage can fly 15 or 20 times, amortizing its manufacturing cost over many missions. The cost of a Falcon 9 launch has dropped to about $67 million, roughly $2,700 per kilogram to low Earth orbit. Individual first stages have been flown more than 20 times. The record as of early 2024 is more than 19 reflights for a single booster. The engineering that makes this possible is subtle and impressive. The first stage must carry enough propellant reserve, about 10 to 15% of its total load, to perform the landing burns, which means it lifts off with extra weight and delivers slightly less payload to orbit than an expendable version. The engines must be capable of deep throttling, reducing their thrust to a fraction of maximum, because at landing the nearly empty stage is so light that even a single engine at full thrust would produce more force than the stage's weight, making a hover impossible. The center engine must throttle down to about 40% of its maximum thrust for the final landing burn, and it must do so with precision because the margin for error is essentially zero. A few percent too much thrust and the stage ascends, a few percent too little and it crashes. The grid fins, 4 waffle-shaped titanium panels mounted near the top of the stage, provide aerodynamic steering during the descent through the atmosphere. They are pushed into the airstream by hydraulic actuators and can swivel to direct the stage's trajectory with remarkable precision. The fins experience extreme heating during the entry burn, glowing cherry red from atmospheric friction, but titanium's high melting point and excellent strength-to-weight ratio allow them to survive. SpaceX's next vehicle, Starship, takes the concept of reusability to its logical extreme. Both stages, the Super Heavy booster and the Starship upper stage, are designed to be fully reusable. Super Heavy is the largest and most powerful rocket booster ever built, powered by 33 Raptor engines burning methane and liquid oxygen, producing a total thrust of approximately 74 meganewtons at liftoff, more than twice the thrust of the Saturn V. The Raptor engine uses a full-flow staged combustion cycle in which both the fuel and the oxidizer are fully gasified before entering the main combustion chamber. This is the most efficient and most complex propulsion cycle ever implemented in a production engine. No full-flow staged combustion engine had ever flown before the Raptor. The Raptor operates at a chamber pressure of approximately 300 atmospheres, the highest of any operational rocket engine. Its specific impulse is about 350 seconds at sea level and 380 seconds in vacuum. These numbers are impressive for a methane engine, though lower than hydrogen engines like the RS-25. The advantage of methane, as I mentioned earlier, is that it burns cleanly, is denser than hydrogen, and can be manufactured on Mars. Starship's landing concept is even more audacious than Falcon 9's. Rather than carrying separate landing legs, which add weight and complexity, the Super Heavy booster is designed to be caught in mid-air by the launch tower itself. As the booster descends to the launch site, it maneuvers to align itself with the tower, and a pair of enormous mechanical arms, nicknamed chopsticks by SpaceX employees, close around the booster, catching it by the grid fins and holding it suspended above the launch pad. This eliminates the need for landing legs, reduces the booster's dry mass, and allows it to be immediately repositioned on the launch mount for refueling and reflight. The concept was successfully demonstrated for the first time on October 13, 2024, when a Super Heavy booster returning from a test flight was caught by the tower arms, a feat of engineering that many observers had considered borderline impossible. The Russian Soyuz, the American Space Shuttle, the SpaceX Falcon 9, and the SpaceX Starship represent 4 fundamentally different philosophies of rocket design, but they all share one thing. They are chemical rockets. They all derive their thrust from the combustion of propellants, the rapid combination of a fuel and an oxidizer, releasing energy that heats the combustion products to thousands of degrees and accelerates them through a de Laval nozzle. And they are all subject to the same fundamental limitation. The exhaust velocity of chemical combustion products is capped at about 4,500 meters per second because the energy available from chemical bonds is finite. This limitation matters because exhaust velocity determines the efficiency of the rocket. The higher the exhaust velocity, the less propellant you need for a given mission, for getting to low Earth orbit, chemical rockets are adequate, barely. For missions to the moon, they require enormous vehicles and leave very little margin for error. For missions to Mars and beyond, they are marginal at best. A crewed Mars mission using chemical propulsion would require many months of travel time, exposing the crew to prolonged weightlessness and cosmic radiation. A mission to the outer planets would take years. A mission to another star is simply out of the question. Even the nearest star, Proxima Centauri, is 4.24 light-years away, and a chemical rocket traveling at the maximum achievable velocity would take roughly 70,000 years to reach it. To go faster, you need higher exhaust velocities, and to get higher exhaust velocities, you need to abandon chemical combustion and turn to other energy sources. The most mature alternative is the electric propulsion engine, a category that includes ion engines, Hall effect thrusters, and various other devices that use electric fields or magnetic fields to accelerate charged particles to very high velocities. The physics is straightforward. Ionize a propellant, typically a heavy noble gas like xenon or krypton, and accelerate the resulting ions through an electric field. The exhaust velocities achievable with electric propulsion are enormous compared to chemical rockets. 20,000 to 50,000 meters per second for ion engines compared to about 4,000 for chemical engines. The specific impulse is correspondingly higher, 2,000 to 5,000 seconds versus 300 to 450 for chemical engines. The catch is thrust. Electric propulsion engines produce exhaust velocities 10 times higher than chemical engines, but their thrust is measured in millinewtons, or at most a few newtons, roughly the weight of a sheet of paper resting on your palm. An ion engine cannot lift a rocket off a launch pad. It cannot even lift itself in Earth's gravity. What it can do is accelerate a spacecraft in the vacuum of space, very slowly for a very long time. Over weeks and months of continuous operation, the tiny thrust accumulates into a significant velocity change, and because the propellant is used so efficiently, the spacecraft can carry much less of it. Ion engines have been used on several deep space missions. NASA's Dawn spacecraft used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres. The Japanese Hayabusa missions used ion engines to reach and return samples from asteroids. ESA's Smart 1 probe used an ion engine to spiral slowly from Earth orbit to the Moon. SpaceX's Starlink satellites use Hall effect thrusters burning krypton for orbital maneuvering. For crewed missions to the outer solar system, where both high velocity and reasonable travel times are required, electric propulsion alone is insufficient. The thrust is too low to achieve the necessary acceleration in a practical time frame. The most promising solution is nuclear propulsion, which comes in two main forms, nuclear thermal and nuclear electric. A nuclear thermal rocket works by heating a propellant, typically liquid hydrogen, by passing it through a nuclear fission reactor. The hydrogen does not burn. There is no combustion. The reactor simply heats the hydrogen to extremely high temperatures, 2,500 to 3,000 Kelvin, and the hot gas is expelled through a nozzle, just as in a chemical rocket. The advantage is that hydrogen, being the lightest element, has the highest exhaust velocity at any given temperature. A nuclear thermal rocket can achieve a specific impulse of about 850 to 1,000 seconds, roughly twice that of the best chemical hydrogen-oxygen engines. Nuclear thermal propulsion is not science fiction. Between 1955 and 1973, the United States tested more than 20 nuclear thermal rocket engines under the NERVA program. The most powerful, the Phoebus 2A, produced about 930 megawatts of thermal power and demonstrated a specific impulse of about 825 seconds. The program was cancelled in 1973, a casualty of post-Apollo budget cuts and shifting priorities, but the technology was proven. NASA and DARPA are currently funding the development of a new nuclear thermal rocket engine under the Draco program, with a planned in-space demonstration before 2030. A nuclear electric rocket combines a nuclear reactor with electric propulsion. The reactor generates electrical power via a turbine, a thermoelectric converter, or some other means, and that power drives an electric propulsion system. The advantage over solar electric propulsion is that the reactor works at any distance from the sun, making it suitable for missions to the outer solar system, where solar panels are ineffective. The Soviet Union flew more than 30 spacecraft with nuclear reactors for power generation, though these were used for radar and other onboard systems rather than propulsion. The United States tested the SNAP-10A reactor in orbit in 1965. Beyond nuclear fission, there are more exotic propulsion concepts that remain firmly in the realm of research. Nuclear pulse propulsion, detonating a series of small nuclear bombs behind a spacecraft and riding the blast waves, was studied seriously under Project Orion in the late 1950s and early 1960s. The concept is terrifyingly crude and astonishingly effective. Calculations suggested that a nuclear pulse vehicle could achieve exhaust velocities of 20,000 to 100,000 meters per second, enabling missions to the outer planets in weeks rather than years. The project was killed by the Partial Test Ban Treaty of 1963, which prohibited nuclear explosions in space. Fusion propulsion, using controlled thermonuclear fusion to heat a propellant, offers even higher performance in principle, with theoretical exhaust velocities of 10,000 to 30,000 meters per second. The problem is that we have not yet achieved sustained controlled fusion for power generation on Earth, let alone in a compact, lightweight engine suitable for a spacecraft. Several research projects are investigating fusion propulsion concepts, but a practical engine is decades away at minimum. Laser propulsion takes a completely different approach. Instead of carrying your energy source with you, you leave it on the ground and beam it to the spacecraft as a laser. The spacecraft carries only propellant or no propellant at all if it uses a light sail that is accelerated purely by the pressure of the laser beam. The Breakthrough Starship initiative, funded by the Russian-Israeli billionaire Yuri Milner, proposes using a gigawatt-class laser array on Earth to accelerate gram-scale probes attached to light sails to 20% of the speed of light, fast enough to reach Proxima Centauri in about 20 years. The concept faces enormous technical challenges. The laser array would need to produce a coherent beam with an effective aperture of kilometers, and the sail material would need to survive the immense power density of the beam without evaporating. But it is grounded in known physics, and serious engineering studies are underway. Antimatter propulsion represents the theoretical upper limit of rocket performance. When matter and antimatter annihilate, they convert 100% of their rest mass into energy via Einstein's E equals mc squared. A kilogram of matter annihilating with a kilogram of antimatter would release about 180 petajoules of energy, roughly the energy content of 43 megatons of TNT. A rocket using matter-antimatter annihilation as its energy source could, in principle, achieve exhaust velocities approaching the speed of light. The practical obstacles are, at present, insuperable. The total global production of antimatter amounts to a few nanograms per year at a cost of roughly $62.5 trillion per gram. Storing antimatter requires electromagnetic containment in an ultra-high vacuum because any contact between the antimatter and ordinary matter results in instant annihilation. These are not engineering challenges that will be solved in the near future. The history of rocketry, from the first Chinese fire arrows to the Raptor engine, is a history of humanity pushing against fundamental physical constraints. The rocket equation is merciless. The chemistry of combustion sets hard limits on exhaust velocity. The structural properties of materials set hard limits on mass ratio. The thermodynamics of heat transfer sets hard limits on how hot you can make a combustion chamber before the walls melt. Every rocket ever built has been a negotiation between ambition and physics, between what the engineer wants to achieve and what the universe will allow. And yet, within those constraints, the achievements have been extraordinary. In the 780 years between the first fire arrows and the first moon landing, humanity went from bamboo tubes of black powder to a machine that could carry 3 human beings 384,000 kilometers from Earth, land 2 of them on another world, and bring all 3 home safely. In the 55 years since the moon landing, we have built space stations, launched telescopes that can see to the edge of the observable universe, sent probes to every planet in the solar system, landed robots on Mars, sampled the surface of asteroids, and just begun to master the art of reusable rocketry. The Falcon 9 booster that lands itself on a drone ship in the Atlantic Ocean is a direct descendant of the V2 that launched from Peenemünde in 1942. The Raptor engine that powers Starship uses the same fundamental physics as the crude rocket motors that propelled Congreve's military rockets in the Napoleonic Wars. The Laval nozzle at the exit of every modern rocket engine is the same converging, diverging shape that Gustave de Laval discovered while trying to make a better cream separator in the 1880s. The continuity is unbroken. The line runs straight from black powder to liquid methane, from bamboo tubes to carbon fiber composite tanks, from unguided fire arrows to GPS-guided autonomous landing systems. What has changed is not the physics. The physics has always been there, waiting to be discovered and exploited, but our understanding of it and our ability to engineer within its constraints. Tsiolkovsky derived the rocket equation in 1903. Goddard built the first liquid-fueled rocket in 1926. Von Braun reached the edge of space in 1942. Armstrong walked on the moon in 1969. SpaceX caught a returning booster with mechanical arms in 2024. Each of these milestones was separated from the last by a period of furious engineering progress, punctuated by failures that killed people and destroyed hardware and broke hearts, followed by painstaking investigation, redesign, and renewed effort. The pattern is consistent, the pace is accelerating. The injector plate of a modern rocket engine is a disc of metal, typically a nickel superalloy, perforated by hundreds or thousands of precisely machined orifices through which the fuel and oxidizer are sprayed into the combustion chamber. The pattern of these orifices, their size, spacing, angle, and arrangement determines how the propellants mix, and how they mix determines whether the engine runs smoothly or tears itself apart. The design of an injector is part science and part art. Computational fluid dynamics can model the spray patterns and combustion behavior with impressive accuracy, but the models are never perfect, and the final design is always validated by test firing, by building the injector, bolting it to a combustion chamber, feeding it propellants, lighting the fire, and seeing what happens. What happens often is an explosion. Combustion instability. The spontaneous development of destructive pressure oscillations within the chamber remains one of the most dangerous and least understood phenomena in rocket engineering. The oscillations can be longitudinal, pressure waves bouncing back and forth along the length of the chamber, transverse, waves bouncing from wall to wall, or tangential waves spinning around the circumference. They can develop in milliseconds and grow from imperceptible amplitudes to chamber-destroying intensities in a fraction of a second. They are triggered by the coupling between the acoustic modes of the chamber and the energy release from combustion, a feedback loop in which pressure fluctuations cause fluctuations in the combustion rate, which in turn reinforce the pressure fluctuations. The F1 engine's combustion instability problem, which I mentioned earlier, was one of the most famous and most expensive engineering challenges of the Apollo program. It consumed years of development time and hundreds of test firings. The solution, a complex injector design with copper baffles that disrupted the transverse acoustic modes, was arrived at largely by trial and error, guided by intuition developed over thousands of hours of testing. No mathematical model of the era was capable of predicting the instability or its cure. Even today, with vastly more powerful computational tools, combustion instability remains a persistent and somewhat unpredictable threat. and engine designers approach it with a respect bordering on fear. The material science of rocket engines is a field unto itself. The combustion chamber and nozzle of a high-performance liquid rocket engine must withstand temperatures exceeding 3000 degrees Celsius, far above the melting point of any known metal or alloy. The solution, as I described earlier, is cooling, regenerative cooling, where the propellant flows through channels in the walls, absorbing heat; film cooling, where a thin layer of propellant is injected along the wall surface; and sometimes ablative cooling, where the wall itself is made of a material, typically a carbon phenolic composite, that slowly chars and erodes, absorbing heat as it does so. Each technique has trade-offs. Regenerative cooling is the most efficient, but requires complex manufacturing. The cooling channels must be machined or formed into the wall with extreme precision, and the wall itself must be thin enough to transfer heat effectively, but strong enough to withstand the internal pressure of the combustion gases. Modern manufacturing techniques have transformed the production of rocket engine components. Additive manufacturing, 3D printing, allows the creation of complex internal geometries that would be impossible or prohibitively expensive with traditional machining. SpaceX uses 3D printed components in its Merlin and Raptor engines. Relativity Space, a newer company, has built an entire rocket structure, tanks, and engine almost entirely by 3D printing. The Super Draco engines on SpaceX's Crew Dragon capsule, the engines that provide launch escape capability, are 3D printed from Inconel, a nickel-chromium superalloy, in a single piece, eliminating welds and joints that could become points of failure. The control systems of modern rockets are orders of magnitude more sophisticated than anything available in the early space age. The V2 used a primitive analog guidance system based on gyroscopes and an integrating accelerometer that measured the rocket's velocity by summing the accelerations it experienced. The accuracy was about 5 kilometers at a range of 300 kilometers, good enough for hitting a city, not good enough for hitting a specific building. The Saturn V used an inertial measurement unit, a set of gyroscopes and accelerometers mounted on a stable platform, coupled with an onboard digital computer, the IBM Instrument Unit, which was one of the first real-time digital control systems ever flown. The Falcon 9 uses GPS, inertial measurement units, and onboard computers running custom flight software that can autonomously adjust the vehicle's trajectory hundreds of times per second, enabling the precise landings that would have seemed like science fiction to the engineers of the Apollo era. The propellant tanks of a rocket are structurally among the simplest components, just large pressurized vessels, and also among the most critical. The tanks must be as light as possible, because every kilogram of tank structure is a kilogram that could have been payload. The walls are therefore made as thin as engineering will allow, often just a few millimeters of aluminum or stainless steel, and the tanks are pressurized to provide structural rigidity. An unpressurized rocket tank is as floppy as an empty soda can and would collapse under the weight of the stages above it. It is the internal pressure of the propellant and the pressurant gas that gives the tank its strength, a design approach called pressure-stabilized structure. The Atlas rocket of the 1950s and 1960s used this approach in its extreme form. Its stainless steel tank walls were so thin, about 4.25 millimeters, that the rocket could not support its own weight when unpressurized. If the tank pressure was lost, the rocket would buckle and collapse like a crushed soda can. One early Atlas did exactly this during ground testing, crumpling into a heap of crinkled metal in a matter of seconds. SpaceX's Starship takes a different approach to tank construction. Its tanks are made of stainless steel, specifically a cryogenic rated alloy called 304L, rather than the carbon fiber composites or aluminum lithium alloys used in most modern rockets. This seems like a retrograde choice. Steel is heavier than aluminum or carbon fiber. But steel has several advantages. It is cheap, it is easy to work with, it is strong at both cryogenic temperatures and the high temperatures of re-entry, and it can be welded rapidly using automated equipment. The use of steel allows SpaceX to iterate its designs quickly and cheaply, building and testing full-scale prototypes at a pace that would be impossible with more exotic materials. Several early Starship prototypes were destroyed during testing, exploding on the pad, crashing during landing attempts, breaking apart in flight, and each one was replaced within weeks. The ability to fail fast and learn fast is itself a form of engineering, and it is one that SpaceX has elevated to an art form. The pace of progress in the last 2 decades has been startling. In 2002, when SpaceX was founded, the company did not exist and Musk had no experience with rockets. In 2006, the Falcon 1's first flight failed 33 seconds after liftoff. In 2008, the Falcon 9 made its first flight. In 2012, the Dragon capsule became the first privately developed spacecraft to dock with the International Space Station. In 2015, the first Falcon 9 first stage landed successfully. In 2018, the Falcon Heavy, then the most powerful operational rocket in the world, made its first flight, carrying Musk's personal Tesla Roadster into an orbit that crosses the orbit of Mars. In 2020, SpaceX became the first private company to launch humans into orbit. In 2023, Starship made its first test flight. In 2024, a Super Heavy booster was caught by the launch tower arms on its return to the pad. This trajectory is not slowing down. It is accelerating, and it is not only SpaceX. Blue Origin, founded by Amazon's Jeff Bezos, is developing the New Glenn rocket and the BE-4 engine, which uses the oxygen-rich staged combustion cycle. Rocket Lab, founded by New Zealander Peter Beck, has developed the Electron rocket for small satellite launches and is working on the larger Neutron vehicle. United Launch Alliance is developing the Vulcan Centaur, powered by Blue Origin's BE-4 engines. China's space program has developed the Long March 5 and is working on a super heavy lift vehicle comparable to Starship. India's ISRO has developed indigenous launch capability at remarkably low cost. The European Space Agency's Ariane 6 is in development. Japan, South Korea, and Israel have all demonstrated independent launch capability. The diversity of approaches and the intensity of competition are unprecedented. For the first time in the history of spaceflight, multiple independent organizations, government agencies, private companies, international partnerships are simultaneously developing launch vehicles, each with different design philosophies, different propulsion systems, different business models. The result is a rate of innovation that has not been seen since the early days of the space race. The fundamental physics has not changed. The rocket equation is as unforgiving as ever. The speed of light is as absolute as ever. The distances to the stars are as immense as ever. But within the constraints that physics imposes, human ingenuity continues to find new solutions, new approaches, new ways to squeeze more performance from the same basic principles. A Chinese soldier in the 13th century, lighting the fuse on a bamboo tube packed with black powder, probably did not think about Newton's third law. He certainly did not think about the Tsiolkovsky rocket equation or de Laval nozzles or staged combustion cycles. He lit the fuse because the device would fly toward the enemy and explode, and that was useful. He was a practical man with a practical problem. But the physics was there in the burning powder, in the rushing gas, in the reactive force that sent the arrow screaming toward its target. It was the same physics that would lift Yuri Gagarin into orbit, that would carry Neil Armstrong to the moon, that would guide a Falcon 9 booster to a pinpoint landing on a pitching deck in the Atlantic. The same physics, the same universe, the same laws operating the same way from the first fire arrow to the last Starship. The engineer's job is to discover those laws, understand their implications, and work within their constraints to achieve things that seem impossible until someone does them. The history of rocketry is the history of that process, the slow, painful, exhilarating accumulation of knowledge, paid for in failures and disasters and occasional breathtaking successes. We started with bamboo and powder, we reached the moon. We are reaching for Mars. The laws of physics say we can go further, much further, if we are clever enough and determined enough and patient enough. The rockets will be different, the propellants will change, the engines will grow more sophisticated, the materials will evolve, but the principle, the fundamental, beautiful, brutal principle of throwing mass in one direction to move in the other will remain the same. It is the only principle that works in the vacuum of space. It is the principle upon which all of spaceflight rests, and the vacuum of space is very, very large and very, very patient, and it will wait for us no matter how long it takes us to get there. The combustion chamber of a Raptor engine during a full-duration test firing contains gases at a temperature of approximately 3,500 degrees Celsius and a pressure of 300 atmospheres. The power released inside that chamber, the rate at which chemical energy is converted into thermal energy, is approximately 11 gigawatts. That is roughly the total electrical generating capacity of a medium-sized country, released inside a metal cylinder less than a meter in diameter. The walls of that cylinder do not melt because the methane fuel at a temperature of minus 162 degrees Celsius is flowing through channels in the walls at a velocity of several meters per second, absorbing heat faster than the combustion gases can deliver it. The temperature gradient across the wall, from the incandescent inferno on the inside to the cryogenic fuel on the outside, can exceed 3,000 degrees in a distance of a few millimeters. The mechanical stresses induced by this thermal gradient are enormous, and they are cycled with every engine start and shut down, fatiguing the metal and eventually requiring replacement. This is the environment in which rocket engines operate. This is what the engineers must design for. The temperatures inside a rocket combustion chamber exceed those at the surface of the sun. The pressures rival those at the bottom of the deepest ocean trench. The flow velocities in the nozzle throat are supersonic. The turbopump bearings spin at speeds that would tear apart any ordinary machine. Every component is operating at or near the limit of what the materials can withstand, and the margins are thin, sometimes terrifyingly thin. It is a testament to human ingenuity that these machines work at all. It is a greater testament that they work reliably enough to trust human lives to them. The RS-25 engine, which powered the Space Shuttle, accumulated more than 1 million seconds of total test and flight time across all units without a single in-flight failure. The Merlin engine that powers the Falcon 9 has achieved a reliability record that approaches and in some respects exceeds that of commercial aircraft engines. These are machines of extraordinary precision and extraordinary violence, harnessing the energy of controlled explosions to hurl metal and humans into the void at velocities that would vaporize them if anything went wrong. Something does go wrong. Sometimes rockets still explode, engines still fail. The Antares rocket exploded seconds after liftoff in 2014 when a turbopump in one of its refurbished Soviet-era NK-33 engines failed. The Falcon 9 was destroyed on the launch pad in 2016 when a composite overwrapped pressure vessel in the second stage oxygen tank buckled under cryogenic loading. A Soyuz rocket carrying a crew to the International Space Station suffered a booster separation failure in 2018, triggering the launch escape system and sending the crew on a harrowing ballistic abort that subjected them to more than 6 Gs. They survived. The rocket did not. Each failure is investigated with meticulous thoroughness. Each investigation produces findings. Each finding leads to design changes, procedure changes, testing changes. The reliability of rocket systems has improved enormously over the decades, but it will never be perfect. The energies involved are too great, the tolerance is too tight, the environment too extreme. Rocketry is not and will never be routine. It is controlled violence on a colossal scale, and the control is always imperfect, but it is good enough to build a civilization in space. Good enough to put satellites in orbit that enable global communication, weather forecasting, navigation, and Earth observation. Good enough to send probes to every planet in the solar system and beyond. Good enough to maintain a continuous human presence in low Earth orbit for more than 2 decades on the International Space Station. Good enough to begin building the infrastructure, the reusable rockets, the orbital refueling depots, the deep space habitats that will eventually take human beings to the moon, to Mars, and perhaps someday to the stars. That someday is closer than you might think and farther than you might hope. The physics does not change, the rocket equation does not relent, the speed of light does not negotiate. But within those constraints, the trajectory of progress points upward, as it always has, as it always will, driven by the same impulse that sent the first fire arrow arcing over the walls of Kaifeng 8 centuries ago, the desire to reach beyond our grasp, to go where we have not been, to see what is there. The night sky is the same sky that the Chinese soldiers saw when they looked up from their fire arrows, the same stars, the same Milky Way. The same vast silent darkness interrupted by pinpoints of light so distant that their photons have been traveling for years or centuries or millennia before they reach your eyes. But we see that sky differently now. We see it not just as a spectacle but as a destination, not just as a mystery but as a challenge, not just as a void but as a frontier, and the machines that will carry us into that frontier are, even now, being built. In factories in Hawthorne and Boca Chica and Kourou and Wenchang and Tanegashima, engineers are bending metal, writing code, testing engines and refining designs. The roar of rocket tests echoes across deserts and coastlines. The glow of welding arcs illuminates assembly bays. The data streams in from sensors and simulations, and the knowledge accumulates, one test firing at a time, one flight at a time, one failure at a time. It has always been this way. It will always be this way. The universe is large, and getting there is hard, and the machines that carry us are the most complex and violent devices our species has ever built. But they work, they fly, they land, and they will carry us further than we have ever gone. The fire arrow flew a few hundred meters, trailing sparks and smoke. The V2 reached the edge of space, the Saturn V reached the moon, the Voyager probes have left the solar system, Starship is being built to reach Mars. The line is unbroken and it stretches forward into a future that we cannot see but are determined to reach. 8 centuries of fire and ingenuity, of black powder and liquid hydrogen, of failures and disasters and triumphs, and an unshakable conviction that the sky is not the limit. The sky is just the beginning. The engines are running, the countdown is underway.